All right, good morning, everybody. My name is Dan Combest. Welcome to the webinar. Today, I'll be talking about improving engineering design with topology optimization. So today's goals for the webinar, I want to introduce ENGYS and some of our adjoint innovations. Hopefully, everyone will learn a little bit more about continuous adjoint and see some of the applications of the software. And by the end of this, you'll obtain a sense of how cases are set up within HELYX, what type of boundary conditions, how we mesh, what kind of the workflow is, and we'll save the questions to the very end. A little bit about ENGYS. We're global providers of CFD products and services. We were founded in the United Kingdom in 2009, and we've always had a focus on enabling open source software in industry, mainly around foam and open foam, and we've been developers since 1999. So if you're familiar with the open foam world, you know that open foam came out around 2006. But before that, we have some of our staff with ENGYS that have had a long time working with that code base. We have 7 offices worldwide, our main office in the United Kingdom, Germany, Italy, here in the US, Australia, South Africa, and in Brazil. We have an established distributor network around the world, so Japan and South Korea. We also have distributors here in the US, France, and Spain. Some of the products that ENGYS offers, the first one is HELYX. This is a general purpose open source CFD software suite. And this can solve a variety of problems: incompressible, compressible, rotating machinery, turbo machinery, and users are able to mesh, set up, solve, and post-process all within the same piece of software. Elements is almost a superset of HELYX in that, in addition to a general CFD software suite, it has tools that are very specific to automotive, like an external aero wizard to help set up external aero cases extremely quickly. We also have HELYX add-ons, and these add-ons include adjoint optimization, block-coupled solvers, a fast marine hydrodynamic solver, and an advanced multi-phase flow solver. Today, I'll be talking about the adjoint add-on. And then finally, HELYX OS. This is an open source GUI for standard open foam that we provide on the internet for free. So if you just Google HELYX OS, you should be able to find that. Or you can always go to engys.com and look around on our website for the links to HELYX OS. So today we'll learn about continuous adjoint, provide a very quick overview, and dive into topology optimization with some test cases and some practical applications. And then I'll perform a demonstration, I'll talk about workflow and go into the case details of this particular case, and then some closing thoughts and talk about some future events. First off, continuous adjoint. Where are the opportunities? You know, it's a great technology, but a lot of people will ask, okay, great, where can we use this? And just some examples: external aero, we could do shape optimization for drag reduction or lift and downforce manipulation if you're in motorsport. Another area of usage is flow control. So if we're doing something with internal combustion engines or HVAC, and you want to target a specific mass flow at several different exits. Also flow uniformity. If you have a case where a uniform velocity profile across a specific boundary is very important, then you can use adjoint and you can use these tools to shape the component so that it delivers a uniform mass flow or flow profile within that specific patch. And then finally, something like swirl control. So if we're looking at internal combustion engines, we may need to deliver a certain amount of swirl into the system. And so here with adjoint, we're able to shape the intake manifold in a certain way to deliver a certain amount of swirl within the system. Another area that might be an opportunity for continuous adjoint is aeroacoustics for noise reduction. We have there's an objective for noise reduction specifically. And one might ask, how would we shape the vehicle in order to manipulate the noise or reduce the noise that's hitting at a certain component on the vehicle? Next, energy and material use. So oftentimes engineers are tasked in the design process to reduce energy of a component or reduce the mass of a component. So lightweighting is a very important task that HELYX Adjoint and continuous adjoint can address specifically. So we can reduce the overall mass of a component by 30%, 20%, 50%. Next is reduction in power losses. So these components may take a certain amount, they'll take a certain amount of energy to push a process fluid through that component. And we're able to optimize based on the idea that we want to reduce these power losses. Just a little bit about continuous adjoint. So there's several key steps, and this is kind of the global view. So initially, with an adjoint computation, first you have to perform a CFD computation. So we're calculating velocity and pressure. And so we'll call these the primal fields. And here we've got the incompressible Navier-Stokes. There's no time derivative, so this is steady state. We might have a source term in here. So we've got a momentum equation with pressure, and then we've got a continuity equation associated with this. After the CFD computation, then we'll actually perform an adjoint CFD computation. And there's analog fields. We'll call these the dual fields. So this is the adjoint velocity, and Q is the adjoint pressure. And it has a similar equation. So it's a transport equation. Again, this is in steady state. There's an adjoint continuity. And this is an overly simplified viewpoint of the adjoint equations themselves, because these equations will change slightly. There'll be different terms based on what the objective is. So the key takeaway from this is that we're performing an optimization by having this analog problem that uses a transport equation in which we're very good at already solving this, because we solve these all the time in a CFD computation. Okay, great. So once we perform the CFD computation, what do we do with that information? We actually compute the sensitivities. And there's two types of sensitivities that we can compute. There's surface sensitivities, which are related to the normal vector or the normal gradient near the boundaries for the primal velocity and the adjoint velocity. So the dot product of those two is related to the surface sensitivities. And then we have another type of sensitivity called volume sensitivity. So this is out in the volume mesh. So one is on the surface and one is out in the volume. What do we do with this information? Well, with surface sensitivities, we're given a color map. And this color map changes based on what the objective is. So for example, if we're trying to have equal mass flow between these four outlets within this manifold, we might be given this color map where red would tell us to push a surface in and blue might say to push a surface out in order to split the mass flow between these four outlets more evenly. Okay, great. What about drag? So here's an external aero case for a vehicle, and red would tell us to push in to reduce drag, and blue would tell us to pull out to reduce drag. And even though there's a color map, there's a sign and there's a magnitude associated with each one of these surface fields. This type of information is ideal for what we call shape optimization. What about volume sensitivities? Well, volume sensitivities tell us information about where we need to free up a volume or where we need to block off a volume. So for example, if we've got pressure drop, say this is the inlet and this is the outlet, here you might suspect that there would be rotational flow. So maybe there's a little bit of wasted energy or pressure losses that might be in this region. So the algorithm is telling us to block off these cells. Same thing for flow uniformity. To create a more uniform outlet, it might predict that we should block off these cells or unblock these cells right here at the very bottom. Now, calculating this, both of these, is a large component of the algorithm, but what do we do with this information? And how we treat this in shape optimization or we treat this in topology optimization if we're using the volume sensitivities is really key to the whole software. So just some further notes on shape versus topology optimization. Shape optimization is used to move the boundaries. The surface physically morphs. So the mesh is changing. It requires smoothing. So the cells near the surface that might be moving, it requires smoothing of those cells near that wall. And if you move enough, it may require remeshing. This is ideal for small deformations. So if we're talking fractions of a millimeter and the lengths get on like a vehicle, this is ideal for this type of situation. And within HELYX, there's two different approaches that we can do. There's a node-based approach, which uses a finite area approach to smooth out the surface sensitivities. And then there's a surface morpher, which takes that information and moves the surface. And then there's also a lattice-based morphing with NURBS where we'll draw a morphing box and be able to offer degrees of freedom to the software to say, this particular panel can move in this direction and move in this manner. So for topology optimization, it's used to block off regions because we're using volume sensitivities. One of the benefits is that the mesh does not change at all. So the mesh is static, so it's much faster. And we don't have to worry necessarily about mesh quality dropping because we've deformed a cell and we've moved a cell. So we don't have to worry about mesh optimization or smoothing in that sense. This is ideal for larger deformations. And you'll see an example of what I mean by larger deformation. And within HELYX, we use a level set immersed boundary to perform this type of optimization. So when I say level set, it's an interface tracking algorithm. So right here, you can see this black line is the level set interface. And level set is the sign distance from a particular free surface. So at level set of 0, that is this black line right here. This isn't color coded, but we would be able to say if the sign was positive or negative, this is solid. And if the sign was opposite of this, then this would be fluid. It uses an immersed boundary to approximate the changing wall flow. And the reason why we like this is because we're able to use smoothers and curvature limiters to produce really high quality surfaces and eliminate things like islands. So for example, if it's a free surface and it grows from a wall, we have better control over maybe an island that would be unmanufacturable developing out in the middle of this flow. So we increase manufacturability of the surfaces by using something like an immersed boundary with a level set approach. So overall, the workflow for the whole adjoint optimization process, first we'll perform an initial evaluation of the current design or packaging space. And this is crucial because it provides a baseline of the objectives to help us really determine the amount of improvement that we've gained. Next, we would do an adjoint optimization and extract those surfaces or extract the morphed surface. And the output of this would be, we would see information about the objective. So we might see the power losses drop, and then we would also have this optimal surface that then we can reuse in the design process. Next, we would do an evaluation of the final design. So these surfaces from the optimization, we tend to re-import them back into the software, remesh, and do things like add layers, add volume refinements, and treat it as a traditional CFD simulation. And we do that to kind of confirm that the optimal surface is indeed an improvement over the initial evaluation. And then finally, the application of this geometry. And at the very bottom here, you can see user must interpret results. So this is a key component in that even though it gives you an optimal design, it's up to the engineer to use their best judgment on what parts of this design they actually want to use. So we'll see an example of that later when I talk about the practical applications. So let me dive into topology optimization and talk about some test cases and some practical applications. So in terms of a test case, This is a fairly straightforward one that we use as a test case. We've got a duct, there's an inlet and an outlet. And this light gray area right here is a three-dimensional packaging space. So this is kind of the maximum volume that this design could occupy. So packaging space, design envelope, some other groups may call it a design envelope if you're doing FEA adjoint, something like that. But this represents kind of the maximum degrees of freedom that we have. Maybe there's another component right here. Maybe we have an immovable duct that we need to connect to right here. Same thing with the inlet. And so if we look at the initial flow pattern, we can see, all right, there's swirl as we pass this area right here. So within swirls, we see, okay, there's going to be power losses. So with this particular case, we wanted to minimize the power losses in the system. And over a few thousand iterations, we were able to reduce the power losses by as much as 50% for this particular operating point. This is a single simulation. We're not setting up 50 cases, 100 cases. This is a single simulation. It's non-parametric. And when I mean non-parametric, I mean we don't have a parametric CAD where everything's related to a standard length. This is a free moving surface. This is the level set interface. And from there, we're able to get there's more degrees of freedom, so the surface is able to move more freely. Let's talk about another example. So that was a single objective. Here's something that's a little bit more complicated. This round component right here, this round patch, this is the inlet. And this represents the initial packaging space. There's more physics. So we've got a porous media. So the porous media is going to be right here in this region. And we've also got a multiple reference frame, which is this fan. So in this particular case, it's pulling air into this box, pushing it through this porous media, and then we've got these three outlets right here. So we want to minimize the pressure losses across the domain. We want to maximize the flow uniformity through the porous media. The reason why we would want to do that is because the more uniform the flow might be through that filter, then the longer the lifetime of that particular product might be, so more durable. And then finally, we want to target the mass flow split between these three outlets. So we want to have equal mass flow between these three outlets right here. And I would go even further and say there's a few other requirements. Another requirement is we don't want to deform our MRF region. We don't want any morphing out here in the inlet region. And we don't want any deformation of our porous media or our outlet ducts. These are fixed and they're connecting to other components. So here we can see the level set evolving over the optimization cycles. We see about a 30% reduction in power losses. And we also see equal mass flow split between these three outlets. If you notice, there's no deformation within the porous media. There's no deformation within the MRF. There's no deformation in these regions right here of the outlet. We do see increased uniformity within the heat exchanger. It's not completely, so there was a little bit of a cost of being able to balance these three and minimize pressure losses of not having necessarily the best uniformity within the porous media. So this is a great example of when you perform a multi-objective analysis or multi-objective optimization, you have to prioritize which one of these objectives matter the most, because we weight the influence of each one of these. So for example, the weight of pressure losses might be 1, and the weight of uniformity might be 0.3, and then the fixed or the constraint that we want to make sure that the three outlets are equal mass flow, that might be a 0.9, something like that. And I'll show exactly how to set that within the software. So those were great test cases. Let's talk about something a little bit more practical. This was a geometry provided by ISON AW. This is a steady state simulation like all the other ones. And this also uses an MRF. The MRF in this gear pump is this rotating gear right here. So we're pulling oil in. The gear is pulling this oil around to the outlet port. So the case was separated into two parts. We have a low pressure and a high pressure. So we've got an inlet port and an outlet port. And just the initial flow field, we can see these streamlines show that they're swirling. And just a note, in this case, we're not morphing in the gear region at all. We want to leave that completely alone because that's been optimized, or that's been designed by that engineer. So we really only want to work in the inlet port and outlet port region themselves. So there's potential. We can already see this. So again, here's our baseline. These are two different optimizations. So for the inlet port, over 100 iterations, or 100 optimization cycles, we were able to see a drop in the power losses. And if we compare the streamlines between the base and the optimized, we can see that there's a reduction in swirling in the inlet port region, and then also a reduction in swirling in the outlet port region. And overall, we saw almost a 19%, so 19% reduction in power losses in this particular system. Next, let's talk about another practical application. This is a BMW N54 airbox from a company called RevDop. The airbox, this particular airbox, was used in a twin turbocharged straight six petrol engine, which was in production in 2006 to 2016. Used in several BMW Series 1, 3, 5, the X6, and the Z4. So it's a big market of users that could have benefited from an improved product. So this particular product, the baseline was the original BMW part. It was scanned and reverse engineered. It has one inlet, which is right here. And then we've got two outlets, these two outlets right here. And there's also an air filter that sits horizontal within this system. This particular case, it was 1.5 million cells that were meshed with HELYX hex mesh, so done within the GUI. The mass flow rate was about 340 grams per second. The two objectives were pressure loss and mass flow split between those two outlets. And then also a curvature objective was applied to the level set equation to increase the manufacturability of the final design. So what RevDop did was they took this information from the adjoint optimization and they were able to improve their airbox. So here's their new shape right here, these two pictures. They were able to provide a 30% reduction in pressure losses and an increase of 16 horsepower, an increase in torque, and not just for that one operating point. So it was able to improve all of the engine RPM, so all of the different operating points that this particular design was meant to work over. This product is out on the market right now, so consumers are able to buy a product that was designed using adjoint optimization. There's other examples of this, but this is one of my favorite that we like to talk about. All right, so let me talk about a demonstration case. How do we set these up? How easy is it compared to if you're already a user of another adjoint software? So here's the particular case. We've got a packaging space, which is this red box right here. And then we've got a 10 meters per second inlet velocity applied to the inlet duct right here. We don't want to morph these outlet duct region. I don't want to morph the patches. I don't want to morph the inlet patch or the inlet duct region. For this case, I'd like to do a multi-objective where I minimize power losses and maximize flow uniformity at the outlet. We want to be able to compare the flow fields, and we also want to be able to extract the optimal surface. All right, so let me dive into that and start here. So this is the interface for HELYX. HELYX is broken up into several different tabs. We've got a mesh, a setup, a solver, and a view tab. And typically the workflow for CFD, for adjoint, for any case that we would perform inside of HELYX, we start with mesh. And so let me first connect to a local host. So when you start the GUI, you're always met with this client server connection. So what client server is is it allows us to either run our case locally, or if we have remote resources that we want to run our case. So this could be a remote resource like a workstation back in my office. It could be a cluster that's on site. It could also be a remote cluster that's like a cloud computing provider. So here, and within here, we can set up different types of connections. This is my office. So let's just do localhost, which will be this Windows machine that I'm working on right now. All right, so let me first start by either I can load up a case that I've already run, or I can start a new case. Let me just start a new case. Let's do duct opt. I want to run this in parallel. This is a fairly weak machine, so let's only do 2 processors. All right, so the first step in this process is to determine our meshing algorithm, so we can use a default approach, which is both are cut cell approaches, and both of them allow us to do volume refinement, adding layers, and lots of different, and zone creation. But the dualized approach ensures 100% layer coverage. For adjoint, we aren't necessarily concerned with layer coverage because we have this bigger packaging space and this optimal surface is evolving. We don't necessarily know where the flow features are going to be, so it's very difficult just off the bat, unless you've run this a few times, to know exactly where to refine. So we typically use a uniform mesh. So I'll use the default, the base mesh. We'll do 0.006, which I've run this before. So let's go to geometry. So the base mesh is a background mesh. We're using a cut cell approach. So what it does is it creates a background mesh. This would create a uniform background mesh. And then where these surfaces that I'm about to import intersect, it will refine according to how I tell the mesher, and then remove the cells outside of the particular zone that the simulation will be carried out in, and then it'll do some smoothing and we'll have a final result. So that's the big picture of how the mesher works. So let's go to geometry. Let me import. Let's go to all right. So here you'll notice that I've got several STL files. So inlet, outlet, inlet duct, outlet duct, and walls. This was split up on purpose because for the most part, when we bring in different STLs, these will become our patches that we can set boundary conditions later on. Okay, so it's important to kind of either have them split up or we can have them as child surfaces. If they're not split, I can use a tool within HELYX to split this up for myself. Okay, so we want a uniform mesh. I'm not going to do any surface refinements. What I will do is I will add just a few layers on the inlet duct region and the outlet duct region to help with the uniformity as it goes to the outlet. And then for the inlet and the outlet, I want to allow those layers to slide up perpendicular to it so I don't get any layer collapse right at this final edge. All right, so the next we need to define a point in space where the simulation is going to take place. And you can either point that if you know the X, Y, and Z yourself, or we can press this button and it will try to guess the center of this device. Okay, great, it's in the middle. And that's all I need to do to generate a mesh. So this takes about 40 seconds to mesh. And the mesher itself, like I mentioned before, is a cut cell approach. And there's several other commercial codes that offer something, a similar approach. And the reason why we like this is because this type of mesher is quality driven. And when I say quality driven, I mean we prescribe a set of metrics: skewness, aspect ratio, the amount of twist that a cell might have. And we provide the mesher with this kind of information because it's an iterative mesher. It will create layers, create refinements, and as it's progressing, if it creates something that would produce a lower quality cell, then it can revert itself and take another path. So for example, like layers, this is one of the reasons why other meshers, other open source meshers might have a lot of layer collapse. So it's a quality driven mesher, and these metrics are determined based on experience with the solvers. And I'd say 98% of the time, these quality metrics, we don't adjust them. There's very few circumstances where we might want to adjust these quality metrics for something like maybe a Lagrangian particle simulation. You might want to have a particular tetrahedral decomposition of the mesh to enable more precise tracking of these Lagrangian particles. All right. It looks like it's almost finished. There we go. All right, if we want to view kind of the surface mesh, very uniform. We can see those layers that are on this pipe right here. They've slid up this outlet. Perfect. That's what we wanted. Now, for most cases, we're going to go to much finer meshes, but for this demo, we're just going to assume that this mesh is going to be fine. Let's go to setup. So in setup, this is where we'll set up all the physics and the boundary conditions and material properties. And like we do in meshing, we start at the top of the tree and we go down. So the solution state is where we set the physics. Is it transient? Is it steady? Is it compressible, incompressible, multi-phase, single phase? Is there energy? Here we're doing segregated, steady. We could do compressible or incompressible with adjoint, but we're going to do incompressible. And then finally, I need to check this adjoint box. And this adjoint box, once I click on something else, it will populate the tree with these 3 more entries. So we're going to use air as our operating fluid, and then modeling. This is where we'll choose the turbulence model. So this turbulence model is the primal. So we want to use a K omega SST. This is kind of the all-around model that I would suggest to use for these types of problems. Next, let's talk about adjoint topology, or sorry, adjoint optimization. Here we have control of our geometry modifier. This is where we can control whether we're going to use a level set approach or we're going to do a node-based approach. For this demo, let's do level set. We can leave the max Courant number and the mean Courant number. We can leave those relatively default. These control the speed at which the level set moves within the system. If we lower both of these, then we'll have more stability, but there's the potential that the simulation may take a little longer. Smoothing radius, let's just choose 0.01. There are best practices related to what this smoothing radius is for the level set. Let me check constant time step, and this basically overrides these 2 right here. But what it does is it will select a more appropriate time step that the level set would take in the system. RMS damping, there's a little bit of smoothing of the sensitivities of what's fed into the level set so that we have a much smoother, more manufacturable level set field that's traveling through. Let me skip down to wall blockage. So I want to prevent level set from growing off of these 2 walls. So let me pick the inlet duct and outlet duct. And there's no cell zones that I want to block off, but I could, if I wanted to, I could make this a cell zone up here and this region a cell zone just to be sure that that wasn't blocked off. Or if I wanted to put a cell zone in here somewhere or mark a specific set of cells that I want to make sure are blocked off, or I want to make sure that they never get blocked, we have that kind of control. Let's talk about adjoint solution. The primal is the Navier-Stokes equation. We do want to execute this. These are controls over the initial time steps of the primal. And then it's very similar here for the adjoint. We do want to execute this. I won't go through all of the settings for this in particular. All of this is in the documentation, which you can find up here in the top right. There's a question mark. or you can also highlight, and sometimes there should be a tooltip for most of these. Okay, great. So normalization type, I want to normalize the sensitivities based on the initial sensitivity after it does initialization of this system. All right, next is the most important part, the adjoint objectives. So here's where we can select exactly what we want to optimize. We have a list of objectives, and I won't go through each one of these. So let me just use power loss. And because this is the most important, I'm going to leave this weighting as 1. Let me go ahead and set the the objective patches to inlet and outlet. However, this particular one will sense the inlet and outlet automatically. I just do that out of good habit. Next, let's do uniformity. And we want to maximize uniformity. Let's do 0.9. We want to maximize uniformity at the outlet. Great. And then finally, let's do one more. Let's do volume reduction. So we want to minimize the volume. And the reason why we do this is that it speeds up the convergence of this surface. So we're kind of pushing the level set to minimize the volume of this component. Let's do 0.1. We're going to do this on all the cells. We could minimize the volume within a particular cell zone if we wanted to. Next, let's define the boundary conditions. So we've got an inlet, and as the slide said earlier, we're doing 10 meters per second. Then there's an outlet. And then for these particular walls right here, we're doing a fixed wall, no slip boundary condition, but I'd like to apply a second order wall pressure to improve the results. Next, cell zones, we don't need to apply anything to cell zones. Numerical schemes, we don't need to control, or we don't need to change any of the gradient, advection, or Laplacian schemes. Solver settings, I don't need to change any of the residuals or apply any velocity limiters. Runtime control, we're only going to run for 500 iterations, and we're going to output every 2 time steps because that'll give us a good view of how this optimal surface is evolving. We're not going to write any additional data. So if you had ENGYS and you wanted to output ENGYS files, we could do that. Field manipulation, we could do things like calculate vorticity as we're running the simulation, or calculate Y+. Monitoring functions, typically I use a lot of monitoring functions. This kind of enables us to monitor the health of the simulation. If we're doing volume refinements, if we're doing a volume report, then we can see things like the min, the max, and the mean. I can just go ahead and show you what that looks like. Let's pick a few fields. Let's just look at primal fields. All right, and so this will look at the min, the max, and the mean for UK and P. Next, field initialization. Let's do potential flow initialization for pressure and velocity, and let's do a Prandtl mixing length approximation for K and omega. So far, everything that I've done, this is very similar to a standard CFD setup for a regular computational fluid dynamics problem, transient or incompressible or multiphase. The only additional thing was I had these 3 sections right here. Now you'll notice I didn't set any adjoint boundary conditions. And the reason why is because the way that things are formulated and the way that the algorithm is set up, we don't have to set any of those boundary conditions. All right, when we're ready to go, we'll hit initialize. And if I've set everything correctly, then I should be just fine. All right, so I see it performing the potential flow initialization. Okay, great. So we could go ahead and just skip to the view tab and look at the initial view or the initial field, the initial condition, or we can go to solver. Let's just go ahead and kick this off and let it start running. This actually takes about half an hour to run, so I'll let it do a few iterations and just walk you through the view tab a little bit. But let's just look at pressure. And if we wanted to, we could do slices, clips, or streamlines. Let's look at a streamline real quick. And for streamlines, let's use the inlet patch as our seed source, and then let's color by velocity magnitude. Let's hit update, and I'll hide all the patches. All right, so right now we can see very nice orderly streamlines. This is characteristic of a potential flow initialization. So there's no viscous forces that are taken into account. So you'll see a big difference once we get the first time step finished. So what's happening right now is that it's performing a primal solve. So it's going to do 1,000 iterations, 1,000 outer iterations of velocity pressure. So traditional steady state primal solve. And it's also going to do a little bit of, it'll solve turbulence in there as well. Then after that, it'll do 1,000 iterations of solving a transport equation associated with power losses. Then it'll do another 1,000 iterations of a transport equation associated with flow uniformity. And then after that, it will output to time step 1. And then we can look at the initial flow field, the initial condition for all of our variables. And then after that, it will perform the 500 iterations of primal solving and adjoint velocity solving. So that will take a little while. Let me cancel this. And then I will load up something that's already been run. All right, let me load this case up. This case is, because it's written so much data, this is a few gigabytes in size. So it has things like streamlines and all the level set data, which we'll look at. All right, great. So let's go to the View tab. Let's move to the first time step. So if you remember those nice, orderly streamlines, let's take a look at the streamlines now, after the primal's been solved, after the initial adjoint iterations have been performed. There we go. All right, so we see lots of swirling. So it's very different from that initial potential flow solution. So this is the real flow field that's happening inside of this particular packaging space. So let's look, let me increase the opacity or decrease it, so you get a sense of what that packaging space looks like. All right, great. So what are a few things that we might want to look at? Well, it's good to have a nice view from the side. So let me create a scene. And so this scene, let's call this side streamlines. And this scene is going to have this surface group, this transparency of these surface patches and also the streamlines. Let me save that. And then next, we want to get rid of the streamlines. We don't need that, but we would like to look at the outlet velocity profile. Let me rescale this. All right, so we want to make sure or look at the uniformity across this patch. So let me save another scene, and we'll call this outlet view and save that. All right, so we should be able to go in between these different views pretty seamlessly instead of having to rotate around. The good thing is that if we're taking screenshots between time steps and you accidentally rotate this, you're able to apply it to the view to get back so that you're able to have consistent screenshots between these different views. So when you're making a presentation or report, it's really easy to see the two. All right, so here's the first time step, and let's go to the last time step. 500. We'll give it a second to reload. All right, great. So much more uniformity. There's a little bit of twisting motion. We'll see a little bit of twisting, but for the most part, the tumbling and rotation, where all the power is being lost of this particular shape that we started with, we've eliminated that. We've reduced it for this operating point. Let's look at the outlet view. All right, so it's much more uniform. So we see a much more uniform color. We could extract this data. We could look at something like a surface report, and we would be able to see a standard deviation of velocity across each one of these cells. So right now, oh, one more thing, sorry. We're able to look at the actual objective output. So over time, we can see the power losses have decreased. We can also see that uniformity increased because we wanted to maximize this. Now we'll see that it maximized and then it dropped off a little bit to another level. The reason why is because we weighted uniformity as less than power loss minimization. So power loss minimization was much more important to us. So it didn't optimize it all the way, but we decreased the weight so that it takes second priority. We're also given things like residuals. We could see residuals of the primal and then also of the adjoint field themselves. So here's the primal, there's uniformity, there is power losses. And again, this is a very coarse case. We would expect slightly different residuals for a much finer case. So overall, we were able to mesh, set up, and solve. And at the end of this, let's go back here. We want to be able to extract this isosurface of the optimal value that level set gave us. Okay, so this is the isosurface of the level set from the adjoint optimization. So I could change this back to the original at time 1, but at that time step, it looks very similar to the packaging space. And we could make a nice video of this evolving over time, over the optimization time steps. So what do we do with this? We can take this, we can export this STL. Let's put this on the desktop. Now, this is just the optimization component. There's several other parts of this whole process. One of the parts would be to bring this back in. So for this case, I've already brought it back in, but it hasn't been meshed. What we would do is we go all the way back to the meshing start, and we would, or the meshing part, and we would re-import our optimal surface. There we would probably increase the refinements. We might even add layers. We would need to make sure that our material point was inside of that, and then we could remesh, and then we could recalculate all of our objectives without morphing, without solving the adjoint equations. We're only solving a primal at that point, just to evaluate what our design is. Then after that, we would use that in the design process. All right, so let me stop here, and let me pick up where we left off. So some closing thoughts. HELYX is a powerful full-featured CFD suite. So we can do CFD, we can do optimization. And HELYX Adjoint adds value to the design process. It has a proven record of industrial application. We have consistent development over the last decade of, adding features that customers want. And as you hopefully saw, it's very easy to use. So we would really love to hear from you about your work, and let's talk about how application could be possible. So what kind of problems would we want to solve? Just a reminder on some of the events, you can go to engys.com/events and you can see some of these events that ENGYS personnel will be attending. We're having another webinar in January, and this one will be on CFD analysis of vehicle aerodynamics with elements. And if you would like to learn more about open source CFD, there's the 15th Open Foam workshop in June of 2020. So you can find out more information about that and find out more information about the events at ENGYS's website. So thank you very much. And I think at this time we can take a few questions.